that clicker. Okay, so to begin with, let's state something that I think most people know, but just for the sake of it, our universe is expanding, and we currently observe it to have accelerated expansion, meaning that the galaxies that we observe are getting farther and farther apart from one another. And the reason why I want to mention this is because there's an important concept of how much radiation, how much matter, how much of a cosmological constant or dark energy there is in our universe that dictates how fast our universe is expanding. So there's this nice relationship between sort of the content, the energy content in our universe and our expansion. And so we can use this type of information to understand what it is that is in our universe at any given time. Okay, so what we know about the universe today is that the vast majority of it is in the form of dark energy, or perhaps a cosmological constant. This is responsible for the present day accelerated expansion of the universe. And why this is a really strange concept is because we know of the things around us. We know that there are galaxies. We know that there are stars and planets. And from just gravitation, we expect those objects to pull together to, attract one another gravitationally. So it's very odd to see that things are wanting to move apart instead. And the reason for that is dark energy. The next most abundant thing in our universe is cold dark matter. So this is responsible for what I would call structure formation. In other words, I need something to create gravitational potential wells for all of our other stuff, our ordinary matter, or what I'll call baryons or atoms, to fall into these gravitational potential wells, to clump, and to eventually give us our stars and galaxies. So cold dark matter plays this very, very crucial role of providing these gravitational potentials in the early universe to give us what we see today. And then, of course, there are photons around, there are neutrinos, so these are essentially in the form of radiation. And then just today, they make up such a small amount of the energy budget that we're not bothering to show it on this pie chart here. But at earlier times, we know that the universe was radiation dominated. So the universe was hotter and in particular smoother. So there's this idea that we can substitute, cosmic time for instead temperature of the universe, the size of the universe, or what I'll call the redshift. So this is the idea that if you have some photon of a given wavelength as the universe expands, it's going to stretch. And the amount that it has stretched, this lambda, this wavelength of observation, minus the wavelength that it was originally emitted at, divided by its emission wavelength, this is what we define as the redshift. So I'll be using, you'll see a lot of this redshift quantity, and I'll give you some markers to understand how big the redshift is at different times in cosmic history. So this is a sort of depiction of the evolution of our universe. So over here at the very far left, we have, a big bang that's followed by a very, very fast accelerated expansion of the universe. This is called inflation. During this time, the universe is very hot, very ionized, very smooth and uniform. And eventually the universe gets to a point where it has expanded enough and cooled enough such that our primordial elements have formed. So this is called Big Bang nucleosynthesis. So we get the formation of hydrogen, of helium, of lithium that results from this. And this occurs, a handful of seconds to a handful of minutes after the Big Bang. And the redshift associated with this is quite high. The next important era in cosmology is the formation of the cosmic microwave background. So this is radiation that we see that comes from a time when all of the ionized particles in the universe have been able to combine and form neutral states. So now we are able to form neutral hydrogen, and then the background radiation is not energetic enough to reionize those particles. And so the universe ends up becoming neutral. And this radiation that's around is able to essentially free stream to us today. Then we enter this period called the Dark Ages. The universe is mostly neutral. There's not a lot of observational handle that we have on this period, and it isn't until cosmic dawn, about 500 million years after the Big Bang, at which we have some hope for an observational handle. So the first stars will turn on at this point, and we can hope to see some signature of that. Now, because we have created stars, the universe can go and become reionized from all the high energy photons that are being emitted from these stars. So this is the process of reionization, and our universe becomes ionized. And then today, of course, we can observe all the different galaxies of different sizes, of different shapes that exist today, about 13.8 billion years after the Big Bang. Okay, so this is the timeline that we have to work with. For the most part, I will focus on this era of the cosmic microwave background. We have exquisite data of the CMB. And so this has really been the initial step into this frontier that we've called precision cosmology, where we're able to say very robust things and very clean things about the universe. And so I'll focus mostly on this, but I will comment a little bit about BBN and galaxies. Okay. So this is a talk about dark matter, and I want to explain to you how we can essentially use these different observations across cosmic time to say something about that. So the first thing that I want to do is motivate just a tiny bit what we are looking for from the particle physics perspective, what we want out of dark matter. Right. This is a very big subject, so I'm going to give you the Cliff Notes version of it. And then I want to give you a few case studies for how dark matter physics can go and interfere with the processes in the early universe and give us something that could be potentially observable, or at the very least, we can go out and search for it and can place constraints on different types of dark matter models. So I'll talk about energy injection. This can be due to dark matter decaying or annihilating into standard model particles. We can talk about, we're going to talk about small-scale suppression due to dark matter that is scattering with ordinary matter. And then I'll say a little bit about how that influences the late-time observations of our galaxies. Okay. So the standard model of particle physics has been well tested, and we are testing it further at higher and higher energies. We have quarks, we have leptons, our gauge bosons that are force carriers, and we have the Higgs, which gives particles their mass. And so the trouble is that I've called this particle that is the topic of this talk dark matter, right? So if it's matter, then I really want to have some sort of understanding of it from a fundamental perspective, like we do our standard model of particle physics. So there's going to be some dark matter particle that I'm going to assume that exists. It could be an entire dark sector. So there could be multiple particles, multiple new forces that completely change the picture and change the phenomenology. So all of this we have to consider when we think about what sort of ingredients are we adding to the standard model to give us this dark matter picture, right? The easiest thing to do is to do things one by one, right? The standard model is fairly complex. The dark sector could be equally complex or even more complex, but we have to start somewhere. So for this talk, I'll assume that there's one dark matter particle that has a specific type of interaction and we're looking for those particular effects. Okay. So the standard story has been the weakly interacting massive particle. So the idea is that you have a standard model particle and dark matter particles, and they're able to interact in some way. So this Feynman-like type diagram is showing you the different ways in which you could take two standard model particles and interact them with two dark matter particles. You could think about annihilating two standard model particles, making two dark matter particles, doing the reverse, annihilating dark matter to make something visible, or scattering between dark matter and the standard model. And so the idea that really kind of gives WIMPs their power is that you can compute how abundant they should be given a specific type of interaction. So what I'm plotting is the dark matter mass divided by the temperature versus the co-moving number density. And the idea is that if you have dark matter annihilations to and from the standard model particles, there will be some equilibrium, right? But eventually, Hubble expansion will take over, and the rate at which you annihilate and form dark matter, that's going to drop off with respect to how fast Hubble expansion is happening. So so eventually, as you follow this distribution of your co-moving number density is decreasing, decreasing, decreasing until some point at which dark matter density sort of freezes out. So Hubble expansion is going to halt the annihilation process, and then however much number density that you have at that time gets frozen in. So the cute thing here is that if we assume, say, annihilation cross-section, a velocity averaged annihilation cross-section times velocity, to have this form, it's going to have some coupling alpha squared, some mass m, and the idea is that we actually get pretty close to the observed relic abundance of dark matter if we just plug in this alpha being the weak scale coupling and this mass to be a weak scale mass, weak as in the weak interaction of the standard model. So this is what's called the WIMP miracle. It's the fact that if we have this freeze out scenario, that it just happens that dark matter that is of the weak scale could explain the amount of dark matter that we have in the universe. And so this is dubbed as the WIMP miracle. And in a supersymmetric framework, a lot of people have thought about over the years possibilities where dark matter could be the lightest supersymmetric particle in some supersymmetric standard model. So this has spawned a large effort to go and search for these WIMPs. Through either production, you could imagine having, colliders. So we have them. We have CERN hosts ATLAS and CMS, for instance. So you can go and look for missing energy, and that's one way of doing it. You can also do something called direct detection, where you're looking for dark matter that exists in our galaxy. Right? It is surrounding our galaxy. It's the dark matter Milky Way halo that hosts the Milky Way. So this is the visible part of the Milky Way, and the Milky Way halo that is made up of dark matter is this huge, much larger object that is providing the gravitational potential for the Milky Way. So we have dark matter all around us, and the idea is that we can build, say, very huge vats of, for instance, liquid xenon, place them far underground, and look for the recoil of, say, xenon atoms from some rare process in which dark matter hits one of these atoms and can be detected. So that's the process of direct detection. We also have the idea of indirect detection, where we're just looking at dark matter annihilation into visible particles, and then we can go and take any number of satellites, I just listed a few here, and say, all right, let's go look for photons to be where we know dark matter is, like, say, for instance, at the center of our galaxy or elsewhere. And we can say, do we observe any excess beyond what we expect astrophysically? And so this is the idea of indirect detection. Okay, the unfortunate news is that these searches haven't really brought any revelations in terms of what dark matter is. We haven't made some sort of definitive discovery. There have been interesting hints in indirect detection, if those of you who are familiar with the galactic center excess story, but nothing definitive from the community as to any positive signal that we would say, ah, yes, this is coming from dark matter. So the idea of looking for this particular WIMP has not borne any fruit. So, but there are other ways of going about looking for possible dark matter interactions. And what better way to look for dark matter interactions than to look in the places that you absolutely know dark matter exists. And so this brings me to what dark matter's role is in the early universe. So I'll briefly go over that concept, and then I'll introduce these different physical processes that dark matter can have. So let's just start with, baseline level cosmological model that we assume that gives us those nice numbers that I told you before. Yes, please. Whether or not the WIMP parameter space is still interesting. So there is still, it depends on how you define weakly interacting massive particle. So I would say that there definitely still is parameter space left. Whether it's going to be experimentally accessible to us is a completely different story. But in terms of, should we be looking elsewhere? This has been the program for, the past couple of decades, that to try to get away from the very simplifying assumptions that led us towards the WIMP in the first place, and to ask, are there any other equally theoretically well-motivated models that could live in this in the universe, right? And so from that aspect, I think it's definitely worthwhile to still go after the WIMP. I mean, the WIMP miracle is a very nice story, and it fits very nicely with everything. But I think we wouldn't be doing ourselves any favors if we didn't look elsewhere as well. So in the early universe, before the CMB formed, dark matter has an important role to play. And these are in the form of what are called acoustic oscillations. So you can imagine having a dark matter potential well here that's due to some amount of overdensity of dark matter. Remember, at this point in time, everything is pretty smooth and uniform, but there are these little fluctuations that happen. So in this region of space, there's more dark matter. In this region of space, there's a little bit less. And I have some baryons that are colored in purple that want to go and fall into this potential well. But of course, there are also photons around that they're strongly coupled to. So there's essentially, you can think about it as radiation pressure wanting to push things out of these wells. And so you can imagine having this scenario on a whole bunch of different scales, and all you have is this nice simple harmonic oscillator picture at different frequencies and wavelengths, and this is just the Fourier space description of what's going on. Of course, things are much more complicated because these are coupled differential equations that we have to solve, but this is the story. So at some point in time, right, neutral hydrogen is able to is able to form, and we recombine, right? So we go through the process of recombination, and the photons are able to free stream. So we get a snapshot as to what the baryons and the photons are doing in and out of these potential wells at the time of recombination. And so, so this is the Fourier space description. If you want a real space, visual of what's happening, so you just have dark matter that these are its density fluctuations over its some sort of mean value, and you can see that not a lot is happening in the dark matter sector, right? These peaks are growing as this animation continues, but the photons and baryons are the things that are doing a lot of in this picture, right? So these are the acoustic oscillations that we see, and these are the acoustic oscillations that are observed in the cosmic microwave background. So this is a map of the CMB. These are temperature fluctuations across the sky. And you know, for satellite experiments, we had COBE in 1992, and so this was the resolution of COBE. About 10 years later, we had WMAP, and then 10 years later, we had Planck. And so the resolution has improved significantly over time. And now the community is going towards ground-based experiments, because to get finer and finer resolution on the sky, you need larger and larger telescopes, but you can only send so large of telescopes into space. So we build them on the ground, so we can make much larger things, get much higher resolution. We don't get full sky coverage, but we can hone in on these tiny little fluctuations. And it's these tiny little fluctuations that's holding all of the information about what's happening in the early universe. So for the CMB, we have measurements of its temperature. It's a black body spectrum, and today the temperature of the CMB is about 2.7 Kelvin. But more interesting are these little tiny fluctuations that we have. So these, this is a power spectrum. So we're asking how 2 points on the sky that are separated by some angular scale, how correlated are those 2 points, are the temperature fluctuations of those 2 points, right? And we average across the sky over all of these different points that are separated by a given angular scale, and thus we get the power spectrum. So we can do this for its temperature. We also have, we can measure the CMB polarization, and we have a spectrum for the polarization as well. So this is the data, and it's binned, but the underlying best fit lambda CDM is our standard cosmological model. Lambda for the cosmological constant, and CDM standing for cold dark matter. This is the best fit lambda CDM curve, and it fits the data very, very well. The error bars are below the resolution of my plotting. So, and once again, dark matter in lambda CDM, it is cold, meaning it's non-relativistic matter. It is collisionless, it doesn't interact with anything else, and it's about 6 times more abundant than ordinary matter. Okay, so this is the standard story. This is the role that dark matter plays, at least at earlier times. So now I want to go and I want to say, well, I want to do some particle physics with this dark matter. What can I do? So the first thing I'll think about is injecting energy, right? So this is akin to the indirect detection efforts that we have today. And so there are a couple things that could happen depending on when you want to inject this energy, right? So let me focus first around Big Bang nucleosynthesis, right? This is the process that's supposed to give us all of our light element abundances and create all of our light elements, so we know how much hydrogen, helium, lithium there should be. So if this process of freeze out happens around an BBN, so in other words, if the dark matter mass is around an MeV, around the mass of the electron, what's going to happen is that there's going to be an amount of dark matter annihilation that's going to transfer energy and entropy from the dark matter into the visible sector, into the photons. And so the amount of radiation density that we have in the total universe, we know is, we have some part due to photons. And this factor over here is accounting for how much is due to neutrinos. So this ineffective is approximately 3, because we have 3 species of neutrinos. And so if you have dark matter annihilation that is altering the content of this rho radiation, then that should have an effect that should be seen. Another thing that can happen is that if dark matter is light enough at the time of BBN, it itself contributes as a form of radiation. And so remember when I said that the expansion rate of the universe is tied to what type of energy content you have at that time. If you've put in more radiation than you expect, you're going to expand in a different way than what we have predicted, what our standard cosmological model predicts. And so during the time of Big Bang nucleosynthesis, there are very important processes that go on that tell us how many protons to neutrons we're creating. And so this conversion process has an impact, or is impacted rather, by dark matter that is light, because you're changing the expansion rate of the universe. So you're changing the time at which the protons and neutrons stop converting. And if you do that, then you change the expectation for how much, say, helium you should have in the universe. And so as you lower this dark matter mass, you can see that, oh, not the predicted helium abundance should be very high, which would be different from our observations, what we conclude from our observations, which is this gray band here. So that allows us essentially to sort of set a limit on this type of scenario. So this is one type of energy injection. Now let's think a little bit later. Let's say we have a different dark matter scenario, and we want to think about what dark matter does at later times, maybe around the CMB and after. So the CMB, the x-axis label got lost. This is redshift. And so the CMB has formed right somewhere around here. So this is the ionization fraction here. How much of the universe is ionized? So it starts very high at high temperatures, at large redshifts, farther back in time. And then the process of recombination has all those ions come and form neutral hydrogen, right? There is some residual amount left over. But if you have dark matter that is just dumping energy into the thermal bath, then what's going to happen is that you're going to, those photons, say, for instance, that dark matter annihilates into, can go and ionize some of the particles that should have just been recombined, some of the hydrogen atoms that should just be neutral. But instead, dark matter can come and ionize them. So you end up with more ions than you would normally expect, right? And so this alters how the temperature evolution looks as well for the matter in the universe. Okay, and so so remember this picture that of our power spectrum, of our temperature power spectrum that we have as a function of multipole. Higher multipole means smaller angular scales. And the effect of annihilations is just to essentially suppress the entire spectrum. And the reason why this happens is that if you have more ions that are around, the CMB photons still see those small residual amount of ions in the universe, and so they can scatter. And so if you have more ions than you expect, more CMB photons are going to scatter instead of free stream. And so that just brings down in total the amount of power that you're able to extract from the CMB. Okay, so that's the effect on the CMB power spectrum. And obviously this is a huge suppression. This is well ruled out, what I've drawn here, because remember the data points from the Planck telescope are small. The error bars are small. The data points lie on this line. So you can draw constraints. So for instance, the Planck collaboration has done this as a function of dark matter mass in GeV. plotting as a function of the cross-section, the annihilation cross-section. And so they have these various different channels of possible dark matter annihilation, but this is sort of a very, very generic model in which dark matter can annihilate with no essentially energy dependence. This sigma v is just constant. And so they are able to draw a line that's kind of hidden underneath all of these colored lines to tell us what the CMB says about dark matter annihilation. And for reference, this is this thermal cross-section. This is the amount of annihilation that, that you want to get this freeze-out story that I was telling you, to get the right relic abundance. So, so you can do this with generic considerations. There's no particular model that went into this fit, but you could also think about having more specific scenarios in mind in which you can set better constraints. And so, for instance, this is work that my student, Gab Montefalcone, finished recently, and this is looking at, say, if dark matter were attracted, specifically wanted to interact with electrons, right? And so you can place a limit on the amount, on the strength of that coupling to electrons as a function of dark matter mass. And so we're able to rule out parameter space that had not been ruled out before for cases in which dark matter is a scalar or a pseudoscalar. So this is just an example about how about how the CMB and energy injection can place limits in very specifically in parameter space of the dark matter models. Okay, so this was the story of energy injection. Let me go ahead and move on to small scale suppression due to scattering. So the other aspect, essentially tilting my Feynman diagram, we don't have to think about annihilation. We can think about dark matter that's just going to come and hit other particles. So if you have now our dark matter potential wells are really made up of like these specific dark matter particles. And when baryons go and acoustically oscillate in these dark matter potential wells, you can think about it as the baryons coming and interacting with one of these particles and kicking it out of its own potential well. And so what that does is that interactions are going to wash out or destroy these small density perturbations of dark matter. And so we can test to see if this happens with the CMB. And the effect that we expect looks a bit different than annihilation with some amount of scattering. The real primary effect is that you get this suppression of the power spectrum as you go to smaller and smaller scales. So the smaller scales you go, the more it suppresses. This is assuming a particular particle physics model, right? And so now I actually have to pay attention to what my particle physics is doing when I create this plot like this. And for dark matter scattering, what matters is something called the momentum transfer cross-section. So you don't have to worry about this, but just know that it's parameterized in the sense of the probability of scattering is going to be some constant times the velocity of your incoming particles to some power. And so in the early universe, the particles that we have access to are your electrons, your protons, your helium atoms. And I can write down different Lagrangians. If you're not comfortable with QFT, do not worry about any of this. The point is that I can write down reasonable particle physics models and map them all to have this type of scaling, where I just take the probability of a scattering event to be some constant times the relative velocity to some power. Okay. So this is the scenario that we have. And what's important, what the universe actually cares about is not the detailed particle physics, right? This is all happening at the on very, very small scales, the universe wants to know what the overall effect is. How much momentum have you transferred in general from between dark matter and, say, baryons? How much energy have you transferred? And this is the important thing. So here I'm just plotting as a function of redshift. So over here at 10 to the 3 is where recombination is going to happen. But I'm plotting the momentum transfer rate. How much momentum do you transfer? At what rate you transfer it? Divided by the expansion rate of the universe. So in other words, if you are above this line at 1, that means your scattering is very efficient. If you are below this line, it means that Hubble expansion is winning. Your particles really aren't able to find one another to scatter and transfer momentum. And so depending on your particular particle physics model that you have that has some particular velocity scaling for this cross-section, you will have different behaviors. You will have different evolution of how much momentum you transfer between dark matter and baryons. And you can do the same thing with energy. At the end of the day, the important part about this is that dark matter has a temperature. And so at early times, you can have a lot of interactions. Everything is very dense, everything is hot. There are a lot of interactions keeping things coupled. And as the universe cools off for most of these models, it just peels off. And dark matter cools in a different way than say the cosmic microwave background does. So with these ingredients, we can go and compute the effects that it has on our normal lambda CDM story and essentially draw constraints on how much scattering is allowed and how much you're able to modify the CMB spectrum. And so here are a whole bunch of limits. We can consider scattering with protons, scattering with electrons, scattering with helium. Those are our options. Limits have been drawn. They span many, many orders of magnitude in the dark matter cross-section as a function of dark matter mass. I don't want you to pay too much attention to the actual numbers here. It's sort of, we really need to place these into some context, and we'll do that a little bit later. But just know that we can do this search. We can actually search for evidence of scattering of this dark matter physics. And if we don't find it, we can then draw exclusion limits. Okay. So this was a story with scattering, and I completely ignored the fact that dark matter could also annihilate. So we can combine, the two stories that I've told you and think about how much scattering do you have as a function of your dark matter mass and what effect that has on Big Bang nucleosynthesis. You can also think about combining the CMB constraints on annihilation at CMB time with the constraints on annihilation that come from Big Bang nucleosynthesis. So these sort of consistent studies can be formed. Okay, so this is mostly focused on the CMB. Let me move now to some other effect that is going to be a consequence of all of this that is happening in the early universe, and think about what happens at later times. So the idea here is that dark matter is going to clump and cluster as the universe evolves, right? It's going to gravitationally attract. And dark matter structures are going to form. So this is a simulation of dark matter particles acting under only a gravitational force. And you're seeing the amount of time since Big Bang count by, and you start seeing all of this wonderful structure, this cosmic web being formed of dark matter. And in areas that have that are particularly bright, this is where there's a lot of dark matter. It's very dense, and so galaxies are going to form there. It's going to attract the normal matter, and stars will start forming. Okay. So this is dark matter's role later on. So if we had something, say for instance, the dark matter scattering story, just suppresses dark matter, these little tiny density perturbations of dark matter on small scales. So if you do that and you have this physics that's in there, that goes and changes this whole picture about how dark matter continues to evolve later in the universe. So we quantify this in terms of what we call the matter power spectrum. And so the matter power spectrum is just telling you what the power is, how much matter there is at particular scales. The scale here is a wave number. It's in units of, unfortunately, small h is about 0.7, but small h divided by megaparsec. Right? So this is the wave number. This is the scale that cosmologists use. And we have a whole bunch of data that are measurements of this matter power spectrum. And this black line is the underlying baseline cosmology that we expect if it's just lambda CDM. So it happens that this portion of the curve over here scales approximately like k cubed. So if we multiply k cubed times this spectrum, it will look very flat at high values of k. So that's what's done over here in this picture. And so there are tons of different dark matter models that you can tune their parameters and you can get interesting features. You can get maybe enhancements at small scales or in our case that we're looking at, we're interested in suppression of small scales. And so all of these different curves for these different models that we won't go into have some particle physics parameter that's controlling how much this deviation from normal lambda CDM is and where exactly, at what scale does that occur. So the idea is that we can test small scale suppression also with galaxy surveys. Because if we suppress the early universe density fluctuations, we wash them out, they're not going to collapse and form structure that we see. So here's some snapshots of an old simulation that just has this generic suppression. So you see this host galaxy, and it has a whole bunch of other points, which are smaller structures that are surrounding it. And if you suppress structure, you'll see the main host galaxy, but you won't see all the little tiny structures around it. So the idea here is that, especially with dark matter scattering, right, I said that there's more suppression the smaller scale that you get. So let's think about what the smallest scale that we can observe dark matter on. What are the smallest objects that we have? And some of the smallest objects that we definitively know about are satellite galaxies of our Milky Way. So here's the visible Milky Way in its spiral arms. And the dark matter halo that envelops it is this enormous circle drawn here. But within our Milky Way, we have satellite galaxies that orbit the Milky Way. And so, these are galaxies in and of their own right, but they are bound to our Milky Way halo. So the sheer existence of these smaller objects means that we can't have some exotic dark matter physics coming into play that goes and suppresses structure to the level that we wouldn't expect to see these objects. We see them, they're there. So some limit has to be placed. And so this is, once again, showing very similar to the curve that I showed before of looking at the suppression of the linear matter power spectrum. This is the power spectrum of some collisional case where you have dark matter that scatters over your cold dark matter scenario. And depending on what your cross section is, how much you scatter, you'll have these different blue-colored curves that are suppressing structure on different scales. Okay, and these scales correspond to some size of a dark matter halo that's able to form. So we observe dark matter halos down to a certain size, a certain mass, and given that, we can place limits on this scenario. And these limits look like the following. So now I'm giving you context. I'm taking one of the CMB curves that I showed you before, plotting the dark matter cross-section with, say, protons, versus the dark matter mass. And so the CMB limit that I placed a handful of years ago is up here. But when we take into consideration the fact that we have this population of Milky Way satellite galaxies, we say that no, we actually can only have a cross-section that's this big, or else it will just, destroy these structures that we see. And so this is in comparison to the story that I told you about direct detection, where we have huge vats of liquid xenon, we place them far underneath the ground, and we search for these rare events of dark matter scattering with one of the xenon particles. So the direct detection bound, this is the upper edge, sensitivity edge of direct detection. Direct detection goes all the way down to about 10 to the minus 46. But direct detection is limited to be in this, higher mass range, and it certainly can't probe too far upwards in scattering cross-section. So these are nice complementary bounds. This is scattering with protons for a very particular case. You can also do the same thing if you want to scatter with electrons, and you can compare it with the direct detection experiments that go and look for scattering with electrons. So this was the story. This was, showing you from early times how, an interaction or two from the side of dark matter, interacting with the standard model in some non-trivial way, can go into effect as times as early as Big Bang nucleosynthesis and alter our expectation of how much helium, lithium we should have in the universe, affecting our CMB, going down and affecting the very galaxies that we actually observe. So, I made very simplifying assumptions. I assumed, right, one dark matter particle. It has a very particular type of interaction, and we can constrain it. But in reality, there are an enormous number of theories that people have in terms of particle physics. And we have this enormous landscape of theories. This was made by my colleague Tim Tate, and this was made over a decade ago, I think now. So the landscape has changed. Some things have been removed and taken away. A whole host of other things have been included. These things have shifted around, but this is just to demonstrate the range of possibilities, theoretical possibilities that we have. And to further emphasize the point, there's an enormous range of dark matter masses that these theories correspond to. Many orders of magnitude in mass the dark matter can take on, and there are various theories associated with different mass ranges for dark matter. And once again, this is already a fairly out-of-date document. This is from 2017. And so there are a whole host of other theories and updates to this slide. I just wanted to show you the vast range of masses that the dark matter theory space covers. And so it might seem hopeless. It might seem, oh my God, we have no idea theoretically what we're looking at, what to do, how do we motivate searches for dark matter? And that has definitely been a question. And we've taken essentially a pragmatic point of view. We kind of divided things up between like very, very, very light dark matter candidates, reasonable, more reasonable. These are masses in that are more comparable to particles that we have and know about. And then there are a whole host of other objects that dark matter could be that's not just a particle. And so we've been systematically attacking this as a field about what are the best ways of going and building experiments, doing particular types of searches. And the nice thing about cosmology, even though we don't get a very controlled lab that we can do quite as sensitive of searches, is that we span an enormous range of scales and an enormous range of energies, right? That we can't obtain in the lab. And so, this is showing redshift versus K, our scale, or you can think about in terms of the mass of the dark matter halo, the dark matter object that we would get. And you can see that there are a lot of different types of probes, right? This is a very schematic view of what the landscape looks like. But, I focused mostly on CMB anisotropies over here, the fluctuations of the CMB temperature. And I also talked about galaxies, our Milky Way galaxies that are in this little tiny corner. But I haven't mentioned any of this other stuff that is going on and is being researched. And all of this sort of fills in the energy and scale axes on this plot. So this is the nice thing. Different observations, they probe different cosmological eras and scales, and therefore they have different sensitivity to different dark matter models. And so this, we're doing these astrophysical observations or cosmological observations regardless for completely other reasons. And it makes total sense to go and say, all right, no, I have my model of dark matter. How can I use this abundance of data that we have in astrophysics to go and say something about the particle nature of dark matter? And importantly, these different observations also have different systematic errors associated with them. So it's always good to have overlap with these different sorts of searches for dark matter. And it's an important thing that when we say like, oh, I have a theory of dark matter, you really need to start at the very beginning, like towards BBN, and run your model down and say, what are all the different effects that it has? And it better be telling a consistent cosmological story for all of these probes that we have across scale and across redshift. So I'm happy to take any questions, but just I want to leave you with the fact that there's still plenty to do in this field. Thank you very much. What are my thoughts on primordial black holes with dark matter? There's a very, very narrow range of, well, relatively narrow range of primordial black hole masses that could constitute all of dark matter. And so it's in this asteroid size range, and there's no particularly compelling reason for primordial black holes of that particular mass range to be made. And so from the theoretical aspect, the only reason why we're potentially interested in model building around this is because we don't have the observations to exclude that region, which I don't find to be a particularly compelling thing to go and say, no, we need to fill this gap. We need observations here. Let's think about ways. I mean, if somebody has a clever way, if somebody has a motivation for why primordial black holes in the form of dark matter should be here, then that's one thing. But yeah, otherwise there's a lot of constraints. And so it's a matter of taste. Do you want to be looking for a candidate in terms of dark matter? Primordial black holes in general, that'd be awesome to find or to see. But in terms of dark matter, how much do you care about 0.01%? depending on where you are in parameter space, of primordial black holes being dark matter. Clearly, that's not the main contributor. But yeah, so it's a bit of a matter of taste. I'm a particle physicist, so I like the particle point of view. Yes. That's a great question. So I think the best way of trying to get at its spin statistics is really going to be in from this point of view that if you have very, very light dark matter, it can only be bosonic. Certainly you can have heavy bosonic particles, and at least with Astro and Cosmo, Astro and Cosmo doesn't particularly care. And there you would definitely want to have more dedicated experiments to go after those types of things. But I think, having this ultralight dark matter where it behaves more like a classical wave than it does a particle is the right way to go about it. And certainly if we have an axion, the axion can still constitute all of dark matter, and so maybe the axion is dark matter, and there are a lot of axion searches going on. But yeah, from a cosmological point of view, it's very difficult to comment on the spin statistics in some really jarring way. The pre-inflationary versus post-inflationary axion story is so the axion this is a misalignment problem. So you have a potential in which you have degeneracy of your vacuum, and then you can create you can tilt it essentially and force the axion to take on a particular value. And then oscillate around that minimum, right? And so these two different scenarios are talking about if the misalignment happens pre or post inflation. And so the phenomenology is slightly different for those. Yeah. Yeah.
You go back to your last slide.
Yeah.
Yeah, I was wondering, so I focused on TNV live and talked about different mechanisms that would change. What would kind of be your smoking gun? Like if you saw a signature or something, let's say a few signals, what would you want to look for? Say, okay, for sure we've seen the imprint of dark matter in some way.
Yeah. Yeah.
Given that there's more than just TNV on the stage, right? Where would you
Yeah. So if you just gave me all the money and gave me all the resources to go and do what I want, 21 centimeter is actually a decent option. So the difference between everything here that's mostly on the left versus mostly on the right is linear versus nonlinear scale. So in other words, are you dealing with things that you can treat dark matter density perturbations as small quantities and you can do a Taylor expansion, or do you have to do this big simulation program that I showed before, where you have to numerically determine how dark matter is forming and clustering into larger objects? So 21 centimeter dark ages and CMB anisotropy work primarily in this regime of which perturbation theory holds. And so they end up being really clean. If you can get nice, crisp data, they end up being really clean probes about the microphysics that's happening at these times. And so 21 centimeter dark ages, we have a lot of radio on Earth, and the atmosphere of Earth further complicates the problem. We also have the center of the galaxy that emits in radio, but we can't do anything about that. So the proposal to get at this dark ages, this period of time that I showed before where nothing is really observationally happening, you can think about going to the far side of the moon. So to get rid of all of Earth's radio emission that we as humans create, and look for this 21 centimeter, this spin flip transition of hydrogen that gets redshifted depending on when the flip happened, and cover the far side of the moon in radio antennas. But that's what's required, and the moon is only so big, right? So you are only going to resolve a certain scale anyway. But it'll beat CMB, or at least current CMB. But yeah, so that would be a really nice clean probe of get to hand me all the money and I can go and build a whole bunch of or somebody can go build a whole bunch of radio telescopes. I think for a lot of these other probes, you would need really, you want to see it in multiple different probes because they all have some nasty systematics that come along with it and degeneracies with astrophysics. That I think is the biggest problem that this community faces. Thank you.